Okay, let's go on to work queues today. The last of the three bottom half interrupt processing handler things. Um, we'll just hopefully get. Hopefully we'll have some time to do some coding too. I already created another branch, and hopefully, with this video, I can also put a link to the diff on GitHub in the description. So let's go. Okay, the old BH mechanism. Although the old BH interface, thankfully, is no longer present in 2.6, it was around for a long time, since the earliest versions of the kernel. Whoa, let me read that again. Although the old BH interface, thankfully, is no longer present in 2.6, it was around for a long time, since the earliest versions of the kernel. Because it had immense staying power, it certainly carries some historical significance that requires more than a passing look. Okay, so not that important to really know this, since the old BH system doesn't exist anymore, but let's just read it for fun for historical stuff. Okay, so nothing in this brief section actually pertains to 2.6, but the history is important. The BH interface is ancient, and it showed. Each BH must be statically defined, and there are a maximum of 32. Because the handlers must all be defined at compile time, modules could not directly use the BH interface. They could piggyback off of an existing BH, however. Over time, this static requirement and a maximum of 32 bottom halves became a major hindrance to their use. All BH handlers are strictly serialized. No two BH handlers, even of different types, can run concurrently. This made synchronization easy, but it wasn't beneficial to multiprocessor scalability. Performance on large SMP machines was subpar. A driver using the BH interface did not scale well to multiple processors. The networking layer in particular suffered. Yeah, so even you had like 10 CPU cores or something like that, back with this old interface, you wouldn't really have things executing, taking advantage of 10 CPU cores because everything was so serial. Other than these attributes, the BH mechanism is similar to tasklets. In fact, the BH interface was implemented on top of tasklets in 2.4. The 32 possible bottom halves were represented by constants defined in Linux/interrupt.h. To mark a BH as pending, the function markBH was called and passed the number of the BH. In 2.6, this in turn scheduled the BH tasklet BH action to run. Before the 2.4 kernel, the BH mechanism was independently implemented and did not rely on any lower level bottom half mechanism, much as soft IRQs are implemented today. Because of the shortcomings of this form of bottom half, kernel developers introduced task queues to replace bottom halves. Task queues never accomplished this goal, so this task queue is the other one that got removed, although they did win many new users. In 2.3, the soft IRQ and tasklet mechanisms were introduced to put an end to the BH. The BH mechanism was re-implemented on top of tasklets. Unfortunately, it was complicated to port bottom halves from the BH interface to tasklets or soft IRQs because of the weaker inherent serialization of the new interfaces. Okay, yeah, because they were written in assumption. These old BH handlers were written with the assumption of single processor or like serialization, and tasklets and software queues are inherently like concurrent friendly, I guess. So it did become harder to rewrite some of these BHs to tasklets. During 2.5, however, the conversion did occur when timers and SCSI, the remaining BH users, finally moved over to soft IRQs. The kernel developers summarily removed the BH interface. Good riddance, BH. Great. Okay, the last one. Last bottom half handler we care about, which is work queues. And again, just to review again, bottom half handlers, they can always be scheduled and raised from top half handlers, interrupt handlers in this case. So choose which one's most appropriate, soft IRQs, tasklet, or work queues. And the chapter at the end is going to probably most likely summarize that, but more or less, the three bottom half handlers just need to, they all kind of in effect do the same thing. They just behave, they do the same thing, but they get the same end result, but behave differently. You choose one. Okay, so work queues are a different form of deferring work from what we have looked at so far. Work queues defer work into a kernel thread. This bottom half always runs in process context. So that's the most important part about work queues, is that it's a bottom half handler that always runs in the context of process. Okay, still in kernel thread, but there's a process associated with it now. So thus, code deferred to a work queue has all the usual benefits of process context. Most important, work queues are schedulable and can therefore sleep. So you can actually kind of use like some sort of semaphore to get some, or yeah, you can use semaphores in the work queue context and not have to like spin and busy wait, because in the other bottom half handlers you had to like spin if you were to lock something, versus in work queue you can actually have something that's waiting for a lock just go to sleep in this case. If that's not clear, we will find out soon. Normally, it is easy to decide between using work queues and soft IRQs or tasklets. So it's easy if we want to decide, okay, do we want to use work queues or soft IRQs or tasklets? Basically, if the deferred work needs to sleep, work queues are used. If the deferred work does not need to sleep, soft IRQs or tasklets are used. Indeed, the usual alternative to work queues is kernel threads. Because the kernel developers frown upon creating a new kernel thread, and in some locales it is a punishable offense, work queues are strongly preferred. They are really easy to use too. If you need a schedulable entity to perform your bottom half processing, you need work queues. They are the only bottom half mechanisms that run in process context, and thus the only ones that can sleep. This means that they are useful for situations in which you need to allocate a lot of memory, obtain a semaphore, or perform block I/O. If you do not need a kernel thread to handle your deferred work, consider a tasklet instead. Cool, so work queues can even like do even bigger things because they are schedulable. Okay? Meaning that they are part of the whole process scheduling flow. Okay, so implementing work queues. In its most basic form, the work queue subsystem is an interface for creating kernel threads to handle work queued from elsewhere. These kernel threads are called worker threads. Work queues let your driver create a special worker thread to handle deferred work. The work queue subsystem, however, implements and provides a default worker thread for handling work. My guess is this is the one that we're going to be using a lot, the default one. Therefore, in its most common form, a work queue is a simple interface for deferring work to a generic kernel thread. The default worker threads are called events/n, where n is the processor number. There is one per processor. So there are worker threads. So we were to go here to maybe btop. We're still left off here. Event. Yeah, I think it's this one. K worker event blah blah blah. So, oops, yeah, k worker, and then you'll have this one here. So like these types of event threads. Okay. Okay. For example, on a uniprocessor system, there is one thread, events/0. A dual processor system would additionally have an events1 thread. The default worker thread handles deferred work from multiple locations. Many drivers in the kernel defer their bottom half work to the default thread. Unless a driver or subsystem has a strong requirement for creating its own thread, the default thread is preferred. Nothing stops code from creating its own worker thread, however. This might be advantageous if you perform large amounts of processing in the worker thread. Processor intense and performance critical work might benefit from its own thread. This also lightens the load on default threads, which prevents starving the rest of the queued work. So like we could create our own worker thread, but always try to prefer using the default thread for our work queue work. So know that creating your thread is an option, but just always prefer this. And I think it's easier to just use the default one. Anyway, so what's the data structure representing these worker threads? Okay, the worker threads are represented by the work queue struct data structure. Okay, so basically every one of these threads has this work queue struct. Okay, and okay, so that's one of these threads, and they all have basically a queue, a work queue. I think this is the number of CPUs. I think it's also implemented as a linked list, has a name. I don't know what single thread feasible in RTR. Let's find out. The structure defined in kernel/workQC contains an array of struct CPU workQ struct, one per possible processor in the system. Because the worker threads exist on each processor in the system, there is one of these structures per worker thread per processor on a given machine. So one of these things here. Okay. I have a feeling this is going to be a lot of thinking. All right. Okay. So we have one of these work queue structs per possible processor on the system. Okay. Now, the CPU work queue struct is the core data structure and is also defined in kernel workqueue.c. So this one here has, I don't know what this NR CPU is. I think that's just the number of CPUs. So this is what one of these things look like. And that looks like each CPU gets its own work stuff, work list, a list of work right here. It's a linked list again. Sure. So note that each type of worker thread has one work queue struct associated with it. Work queue struct, which is this one. This is the current, and then basically the linked list is probably chaining up all this to get each individual work struct. And that represents an entity in the work queue. Okay. Let's see. Inside there is one CPU work queue struct for every thread. Okay, so one of these, okay, for every thread, and thus every processor, because there is one worker thread on each processor. So this one, okay. Data structures representing the work. All worker threads are implemented as normal kernel threads running the worker thread function. After initial setup, this function enters an infinite loop and goes to sleep. When work is queued, the thread is awakened and processes the work. When there is no work left to process, it goes back to sleep. The work is represented by the work struct structure defined in Linux/workqueue.h. So We've already seen workQ.c. We're going to have workQ.h, which defines this is going to be our, like, the most interesting struct here. This represents literally the work that we're going to do given by this function handler here. So these structures are strung into a linked list, one for each type of queue on each processor. So yeah, it makes sense, right? Queue, linked list, they're kind of tied together. For example, there's one list of deferred work for the generic thread per processor. When a worker thread wakes up, it runs any work in its list. As it completes work, it removes the corresponding work struct entries from the linked list. When the list is empty, it goes back to sleep. So this is how it's actually processing things. An infinite for loop. Basically, if this is empty, it'll just put itself back to the run queue. Otherwise, we run stuff. Okay. Finish wait. So this function performs the following things in the infinite loop. The thread marks itself as sleeping. So this one, prepare to wait. Task interruptible. And sets its state to task interruptible and adds itself to the wait queue. And the wait queue is that queue in the scheduler that has all the processes that are sleeping, right? So we have the run queue, which is active running tasks. Then we'll have the ready queue, basically all the processes that are ready, and then wait queue. I think those are the ones that are blocked or sleeping in this case. Blocked on IO or sleeping. So if the linked list of work is empty, the thread calls schedule and then goes to sleep. If the list is not empty, the thread does not go to sleep. Instead, it marks itself as task running and removes itself from the wait queue. And I think this is what it does, finish wait. Okay, finish wait is number 3 here. And then if the list is non-empty and if the list is non-empty, the thread calls run work queue to perform the deferred work. So call run work queue to perform that deferred work. Okay, so now let's take a look at this function here. What's inside here? What's the meat of this function? And this is going to be the while loop here. The function run work queue in turn actually performs the deferred work. So notice how it's getting that work struct, this one right here, while the list isn't empty. This work struct is this definition here. Notice this func here, which is going to be the handler. So we look down here, let's find that. So struct work func t. So f is going to be assigned to work func, and then notice how it just calls a function with the work. So that takes in, so going back here, this function, work func t doesn't have that definition, but most likely it's going to take in the entire work struct right there. Okay, so let's read what it does. This function loops over each entry in the linked list of pending work and executes the func member of the work queue struct for each entry in the linked list. While the list is not empty, it grabs the next entry in the list. Okay, so while the list is not empty, it basically grabs the next entry in the list right here. It retrieves the function that should be called func, okay, and its argument data. Okay, so then it removes this entry from the list right here, removes it, and clears the pending bit on the structure itself. Okay, work clear pending. And then it invokes the function right there. And then we repeat. Cool. While the list is not empty. Okay. So, work queue implementation summary. The relationship between the different data structures is admittedly a bit convoluted. Oh yes, it is. Yeah. This one's the hardest one so far, I think. Figure 8.1 provides a graphical example which should bring it all together. So you have that worker thread that is one per CPU. Each one has a CPU work struct. And then we have a work queue belonging to the CPU work struct. So one of these threads per processor. Okay, then you have one per type of worker thread. So we have one in a default by default. And then each one has a list of these work structures. Okay. And in the CPU work struct, you have these guys here. Sure. At the highest level, it's a good thing. I think most of the time as driver writers, they're just gonna have to know how to queue work, like create work, queue work. I don't think like this is like the architecture of how the work queues work. So I wouldn't worry too much as since we're still unfamiliar. I think sometimes when learning new systems and code, learning how to use a system is like a great first start as opposed to like not really using it and then trying your best to understand it. It's really hard to do that. So I think the focus should be more like we should learn how to use the work queues first, and then if we care enough, let's dive into detail how this actually truly works. So I'm not gonna stress too much. At the highest level, there are worker threads. There can be multiple types of worker threads. There is one worker thread per processor of a given type. Parts of the kernel can create worker threads as needed. By default, there is the events worker thread. Each worker thread is represented by the CPU work queue struct structure. The work queue struct structure represents all the worker threads of a given type. For example, assume that in addition to the generic events worker type, you also create a Falcon worker type. So that's just an example. So there's an extra worker type which is called Falcon instead of the default events. So you have two types. Also assume you have a 4 processor computer. Then there are 4 events threads, okay, and 4 Falcon threads, and thus another 4 CPU work queue structures. There is one work queue struct for the events type and one for the Falcon type. Oh, okay. So this is one per type of worker thread. Okay, so we had Falcon and events, then there's 2 versus we only have 1 here for each CPU. Okay, good. I'm starting to get this. Okay, so now let's approach from the lowest level, which starts with work. Your driver creates work which it wants to defer later. The work structure represents this work. Among other things, this structure contains a pointer to the function that handles the deferred work. The work is submitted to a specific worker thread, in this case a specific Falcon thread. So that's the example worker thread. The worker thread then wakes up and performs the queued work. Most drivers use the existing default worker threads named events. They are easy and simple. Some more serious situations, however, demand their own worker threads. The XFS file system, for example, creates 2 new type of worker threads. Cool. All right, let's get into code. I think we're almost there to be able to code something using work queues. And I like this first sentence so far. Using work queues is easy. We cover the default events queue first and then look at creating new worker threads, which I don't think we'll probably do here. We'll just kind of just use the work queue. Yeah. So creating work. The first step is actually creating some work to defer. To create the structure statically at runtime, use declare work. Okay, so it's a runtime thing. So just a little bit more different than tasklets in this case. Okay, but more or less the approach is similar. This statically creates a work structure named with handler function func and argument data. Alternatively, you can create work at runtime via a pointer. So this is the dynamic way to do it. Okay, with init work. This dynamically initializes the work queue pointed to by work with handler function func and argument data. Okay, and then we need a handler. The handler here, that's a signature, just like how it was expected right there to be passed in. The The prototype for the work queue handler is void work handler pointer to avoid data. A worker thread executes this function, and thus the function runs in process context. By default, so yeah, remember this function is running in process context. By default, interrupts are enabled and no locks are held. If needed, the function can sleep. Note that despite running in process context, the work handlers cannot access user space memory because there is no associated user space memory map for kernel threads. The kernel can access user memory only when running on behalf of user space process. So it's running on user, like in process context, but there's no user space process like running associated for this specific worker thread or work in the work queue being executed. So it's not the same like a system call. Such as when executing a system call, only then is user memory mapped in. So yeah, can't find anything there if you're on a work queue handler. So locking between work queues or other parts of the kernel is handled just as with any other process context code. This makes writing work handlers much easier. The next two chapters cover locking, next two being chapter 9 and chapter 10. Okay, so now we have our work, right, created. Work is created, basically creates the work struct, that work underscore struct. So this one here. Then we gave it the handler by having this implemented. Now we want to schedule it. Basically, where are we going to schedule our work queue, like our queued up, well, how do we queue up some work into the work queue? And that's from, again, our any top half handler using this API here. So let's read that. Scheduling work. Now that the work is created, we can schedule it to queue a given work handler's function with the default events worker thread. Simply call schedule work with the pointer to that work struct. The work is scheduled immediately and is run as soon as the events worker thread on the current processor wakes up. Okay. Sometimes you do not want the work to execute immediately, but instead after some delay. In those cases, you can schedule work to execute at a given time in the future. Schedule delayed work delay. In this case, the work struct represented by the address of work will not execute for at least delayed timer ticks in the future. Using ticks as a unit of time is covered in chapter 10. Okay. So flushing work. Queued work is executed when the worker thread next wakes up. Sometimes you need to ensure that a given batch of work has completed before continuing. This is especially important for modules, which almost certainly want to call this function before unloading. Other places in the kernel might need to make certain no work is pending to prevent race conditions. For these needs, there is a function to flush a given work queue to clear it. So flush scheduled work. It takes in no arguments. This function waits until all entries in the queue are executed before returning. While waiting for any pending work to execute, the function sleeps. Therefore, you can call it only from process context. Okay. So basically, it's just going to force a run on all the work inside the work queues. That's what it means to flush. Okay, so note that this function does not cancel any delayed work. That is, any work that was scheduled via scheduled delay work and whose delay is not yet up is not flushed via flushed scheduled work to cancel delay work called. Okay. So yeah, it doesn't cancel, it just runs all to completion. Okay, if you really want to cancel delay work, you do cancel delayed work with that work struct passed in. This function cancels the pending work, if any, associated with the given work struct. Okay. Okay, so let's finish this section here. Okay. Creating new work queues. If the default queue is insufficient for your needs, you can create a new work queue and corresponding worker threads. Because this creates one worker thread per processor, you should create unique work queues only if your code needs the performance of a unique set of threads. So again, one of those things that sounds kind of discouraged, but the tone kind of makes it iffy if that's the case. You create a new work queue and associate worker threads via a simple function. Struct work queue struct create work queue with a name. The parameter name is used to name the kernel threads. For example, the default events queue is created via something like this. Okay? This function creates all the worker threads, one for each processor in the system, and prepares them to handle work. Creating work is handled in the same manner regardless of the queue type. After the work is created, the following functions are analogous to schedule work and schedule delayed work, except that they work on a given work queue and not on the default events queue. So these two, same thing, queue work and queue delayed work. We'll take in your work queue struct that you had created and then the type of work. So it's just telling, oh, hey, schedule this work inside this work queue. Okay? And then the delayed version just has the delayed one. So finally, you can flush a wait queue via a call to a function flush work queue with that work queue given as an argument, or at least the location, the reference to it. As previously discussed, this function works identically to flush scheduled work, except that it waits for the given queue to empty before returning. Okay, let's just work through an example. So I have here branch work queues, and we're going to do the same thing. Like, what are we going to do? So we're going to use our friend, right? Goal again. Schedule work to be done in the I8042 interrupt handler. Using work queues. Okay. Again, we're going to create two files. We're going to do average dev.h and then average dev.c. This one is going to so this one is different. This macro of like, for example, declare work is different in that you have to give it the name, the variable name of the struct that you want, and then your handler. So if we were to look in code, declare work, it works a little different for sure. So while that's going. Okay, so this one is declared differently. Where is it? I don't remember where it would be. Oh, it's probably in work queue H. Let's see. Probably in work queue H. Yeah, let's go to work queue H. And there we see declare work. Okay, yeah, so here. So crap. Okay, so notice how this takes in two arguments. So I think the book is already wrong. It had like 3 arguments here. But it's like 2 arguments, the name, okay, and the function. And notice how it rewrites, the macro rewrites to this struct declaration with n here. Okay, so average dev.h should probably export or not export, but like define this one so that it can be accessed elsewhere. Specifically, our i8042 interrupt handler. So basically, we're just going to make sure that's the case here where we have access to this struct, because declare work, when we call this somewhere down the line, it's just basically kind of just saying struct work struct n equals to whatever this is. Okay, so this actually doesn't return anything. It just rewrites it to this sort of declaration and definition of this n work struct, whatever you gave here. So that then means that we need to declare a work struct, a struct work struct. Come on. Struct work struct. Okay, so we just need to declare that, and then average dev.c will call declare work and implement handler. Okay. After that, once we have that, we make sure average dev.c is compiled by updating again. Oops. The makefile of where i8042.c is in. Okay. Finally, we should update i8042 interrupt function in i8042.c to schedule work with the struct work struct declared in average dev.h. So we have to include that. Okay. Compile. So that's as far as we thought. So we need two files. We just declare them and implement them, and then add them to the make file. Make sure average dev.h is in the include Linux directory. Then just update i8042 again to just schedule that bottom half handler and see what happens. Okay, let's get started. So first off, where am I going to be? I am going to go to interrupt.h. Actually, I'm already at the right place, include Linux. So let's create a file there. So e%h/average dev.h. And this should be pretty simple. We just do if and def underscore Linux average dev h define underscore Linux average dev h and diff. Then what we want to do is we also want to include the interrupt stuff. So include Linux interrupt.h, and then we want to just do struct work struct, something like this. Struct work struct average dev work. So we're just defining that work struct here to exist, so that if we were to include the header, we have access to this struct here, we're gonna use this struct. We're gonna we're gonna define it in average dev.c. Right now we're just declaring it. So far so good. It's as simple as that. And then let's go to in this case i8042.c. Somewhere here, where you see this directory here. Let's just create the average dev file, average dev.c file there. So same thing. Okay, so this one we just need to include average dev.h. Oops, linux/average dev.h. And then let's just implement like the handler, which basically is something like this: void work handler void data. So then I can just say something like static void average dev work handler, takes in a pointer to a void. And then let's do something interesting. Let's just, I don't know, loop for like 1,000,000 times or something. So let's do in I, and then we go while this is I equals 0, just initialize, while I is less than, I don't know, 1,000,000. Don't know how fast it's gonna go. Just pretty much do nothing. Okay. Do nothing, and then finally print k kern info. Let's just do average dev after busy waiting. Okay. Actually, there's just one more. Throw one more to this. Okay. So we print k, and then that's about it for now. Okay. So then we also need to declare work. So we just simply need to do something like this. And then what was it? What do we declared? Was it work queue average dev.h was average dev work. Okay. So average dev work, and then the handler, which will be average dev work handler, and that is how we do it. Okay. So that ends up being struct. This will kind of just, after the preprocessor runs, expands to that definition that looks something like this one, this declare work right here. So it'll be like struct work struct average dev work equals work initializer and blah, 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 blah. Okay. So then now, hold on. Let me see if I got the right types. Work struct. Yeah, okay. Okay, so now let's update our make file. So we're still here anyway. So we can do, what's it, drivers input serial.makefile. Same thing where i8042 is. We can just go here and do average dev.o. So by now it's like I'm kind of getting good at this because I've done it several times already with the tasklets and stuff. Now we just need to update i8042.c. So you get used to the code base eventually. And then it's called i8042 interrupt. Yeah, I'm getting used to it, getting faster. Okay, right here. This is where we want to be. So once we get the data, why not? Let's just say here, let's have something that tells us that some keyboard thing happens. So we do print k here, average dev, current info, average dev, some i8042 interrupt occurred. Okay, and then we can just do something like, well, in this case, we gotta go back up here and then actually include the average dev header. So because we need that, we need to schedule the work, and the work struct is in average dev.h. So we just do something like that. And then if we were to go to here again, we could use schedule, is it schedule work? Yeah, schedule work with that pointer to average dev work. And then that does stuff. Okay. That should be it. Let's see what happens. So actually, let me make sure that I have saved everything. Okay. Okay. For sure. Okay. Now, once we have that, we can do make J24 again. 24 threads. Hopefully I don't have any compile errors. Okay, so I actually started compiling and then realized that there was a syntax error. I forgot to type extern here to kind of declare that struct, but then I ended up compiling and it seems okay. I installed it, so then sudo reboot. Okay, I did see some logging right here. Some interrupt occurred, and then there was like there should have been some busy waiting. So well, no keystrokes happened yet. So did I plus plus? I probably didn't either. That's probably even another bug. Oh my god. Ha! Did nothing, so it's infinitely spinning. All right. Well, that's smart. Okay. Let's go to our old kernel and recompile that. I got so excited typing that I forgot the I++. All right, so yeah, we're in a bad state right now, right? But that's fine. We just need to boot into a different kernel that we have backed up. So all good. Just need to do it again. Wow. Okay. I feel like our custom kernel like boots up faster. Okay. Less modules to load most likely. Okay, so we just need to recompile with our fix. See, we fixed the bug. Make J24, and I'm gonna pause this again. Okay, I'll compile the sudo make install, and just like for good measure, I think we should just update grub. I don't know. Never tried it that way. Oh. Okay, and then sudo reboot. So we should have still have our changes. This time I incremented I. That's silly of me. Hey. Things happened. Remember I was like busy waiting, and then I didn't have like this even incrementing, right? So it was an infinite loop. What's even worse is that I had like something like 10 million or 100 million or something like that, and actually that was causing the kernel to not boot because it was in this like state where it was like trying to do so much work. So I reduced that to just 100,000, and after rebooting and compiling and everything again, I actually have something here. So after I type some sort of keystroke, right, we actually get some busy waiting occurring, and yeah, I can actually like feel some of it too. Let's see if we were to go to system monitor, do we see CPU just like spiking? Let's see. So if I just do this, right, I should see some CPU like kind of just spiking eventually. So Yeah, I do see like CPU 3 once in a while. Oh, CPU 2 too. So I just like kind of just do this. Let's see, eventually, I guess based off of sampling, you'll see some CPU activity. Um, let's see. Yeah, little spikes here and there. So yeah, that's a quick change for I guess work queues. Um, Probably gonna have to edit this video to make sure I'm not confusing. Anyway, let's go on. So we're all the way down to here. So the old task queue mechanism, like the BH interface, which gave way to soft IR queues and tasklets, the work queue interface grew out of shortcomings in the task queue interface. The task queue interface, often called simply TQ in the kernel, like tasklets, also has nothing to do with tasks in the process sense. The users of the task queue interface were ripped in half during the 2.5 development kernel. Half of the users were converted to tasklets, whereas the other half continued using the task queue interface. What was left of the task queue interface then became the work queue interface. Briefly looking at the task queues, which were around for some time, it is a useful historical exercise. Task queues work by defining a bunch of queues. The queues have names such as the scheduler queue, the immediate queue, or the timer queue. Each queue is run at a specific point in the kernel. A kernel thread, called kEventD, ran the work associated with the scheduler queue. This was the precursor to the full work queue interface. The timer queue was run at each tick of the system timer, and the immediate queue was run in a handful of different places to ensure it was run immediately. Hack. There were other queues too. Additionally, you could dynamically create new queues. All this might sound useful, but the reality is that the task queue interface was a mess. All the queues were essentially arbitrary abstractions scattered about the kernel as if it was thrown in the air and kept where they landed. Okay, so it basically means that you just gave too much power to the implementers, and they just all started to do their own thing. The only meaningful queue was the scheduler queue, which provided the only way to defer work to the process context. The other good thing about task queues was the brain-dead simple interface. Despite the myriad of queues and the arbitrary rules about when they ran, the interface was as simple as possible. But that's about it. The rest of the task queues needed to go. So they don't exist anymore either. The various task queue users were converted to other bottom half mechanisms. Most of them switched to tasklets. The scheduler queue users stuck around. Finally, the kEventD code was generalized into the excellent work queue mechanism we have today, and task queues were finally ripped out of the kernel. And yes, it is in a way excellent because it's pretty simple. Again, like all you have to do is just declare this, work struct, and then implement it in some other file, or maybe on the same file. Implement a handler, and then call declare work with your work queue struct and the handler as arguments to this declare work macro. And somewhere in your interrupt, just implement this or just call the schedule work with that pointer to the work queue struct that you had. So it's not too bad. Which bottom half should I use? The decision over which bottom half to use is important. In the current 2.6 kernel, you have three choices: soft IR queues, tasklets, and work queues. Tasklets are built on soft IR queues and therefore both are similar. The work queue mechanism is an entirely different creature and is built on kernel threads. Soft IR queues by design provide the least serialization. This requires soft IR queue handlers to go through extra steps to ensure that shared data is safe because two or more soft IR queues of the same type may run concurrently on different processors. So yeah, again, soft IR queues, you can have multiple running same time. Tasklets, not exactly the same way, just that it's the same way, but tasklets of the same type won't run at the same time. So if the code in question is already highly threaded, such as in a networking subsystem that is chest deep in per processor variables, soft IRQs make a good choice. They're certainly the fastest alternative for timing critical and high frequency uses. Tasklets make more sense if the code is not finely threaded. They have a simpler interface, and because two tasklets of the same type might not run concurrently, they are easy to implement. Tasklets are effectively soft IRQs that do not run concurrently. A driver developer should always choose tasklets over soft IRQs unless prepared to utilize per processor variables or similar magic to ensure that the soft IRQ can safely run concurrently on multiple processors. Now finally, if your deferred work needs to run in process context, your only choice of the three is work queues. If the process context is not a requirement, specifically if you have no need to sleep, soft IRQs or tasklets are perhaps better suited. Work queues involve the highest overhead because they involve kernel threads and therefore context switching. This is not to say that they are inefficient, but in light of thousands of interrupts hitting per second, as the networking subsystem might experience, other methods makes more sense. For most situations, however, work queues are sufficient. In terms of ease of use, work queues take the crown. Really? Okay. Using the default events queue is child's play. Okay, next come tasklets, which also have a simple interface. I actually thought tasklets were easier, but okay. Coming in last are soft IRQs, which need to be statically created and careful thinking with their implementation. Oh, I guess this is in the perspective of like if you were to do this dynamically. We've only been doing it statically, which is why it feels all the same. Table 8.3 is a comparison between the three bottom half interfaces. So interrupt context, because these are kind of like the same thing, soft IRQ and tasklets, whereas work queues run in process context because they are different than soft IRQs. And yeah, their soft IRQs are naturally parallel concurrent friendly. Same thing with work queues. Tasklets only concurrent friendly on tasklets not of the same type. That's what inherent serialization means. Okay. In short, normal driver writers have two choices. First, do you need a schedulable entity to perform your deferred work? Fundamentally, do you need to sleep for any reason? Then work queues are your only option. Otherwise, tasklets are preferred. Only if scalability becomes a concern do you investigate soft IRQs. So it's like we always talk about three options. Three options is really two. It's either tasklets or work queues in this case. Locking between the bottom halves. We have not discussed locking yet, which is such a fun and expansive topic that we devote the next 2 chapters to it. Nonetheless, you need to understand that it is crucial to protect shared data from concurrent access while using bottom halves, even on a single processor machine. Remember, a bottom half can run at virtually any moment. You might want to come back to this section after reading the next 2 chapters if the concept of locking is foreign to you. One of the benefits of tasklets is that they are serialized with respect to themselves. The same tasklet will not run concurrently, even on 2 different processors. This means that you do not have to worry about intra-tasklet concurrency issues. But inter-tasklet, so tasks between other tasklets, concurrency requires proper locking. So when 2 different tasklets share the same data, which is totally possible, that's when you need to care about locking. That's when concurrency becomes an issue for tasklets. Because soft IRQs provide no serialization, even if 2 instances of the same soft IRQ might run simultaneously, all shared data needs an appropriate lock. So you have to take care of this locking if it comes down to having to work with shared data. If process context code and bottom half share data, you need to disable bottom half processing and obtain a lock before accessing the data. Doing so ensures local and SMP protection and prevents a deadlock. If interrupt context code and bottom half share data, you need to disable interrupts and obtain a lock before accessing data. This also ensures both local and SMP protection and prevents a deadlock. Any shared data in a work queue requires locking too. The locking issues are no different than from normal kernel code because work queues run in process context. Okay, so it's like a system call kind of thing. Chapter 9, an introduction to kernel synchronization, provides a background on the issues surrounding concurrency, and Chapter 10 covers the kernel locking primitives. These chapters cover how to protect data and bottom halves use. Okay, how much do we have left? Oh, okay, let's just do it. Let's blaze through it. Okay, disabling bottom halves. Normally, it is not sufficient to only disable bottom halves. More often, to safely protect shared data, you need to obtain a lock and disable bottom halves. Such methods, which you might use in a driver, are covered in Chapter 10. If you are writing core kernel code, however, you might need to disable just the bottom halves. To disable all bottom half processing, specifically all soft IRQs and thus all tasklets, call local bh disable. Okay, so this is bottom half disable, not like the bottom half that they removed. To enable bottom half processing, call local bh enable. Yes, the function is misnamed. No one bothered to change the name when the BH interface gave way to soft IRQs. Okay, so basically disable soft IRQ and tacit processing on the local processor. Okay, I'm guessing we don't really need to do that often, and enable it. Okay. The calls can be nested. Only the final call to local BH enable actually enables bottom halves. For example, the first time local BH disable is called, local soft IRQ processing is disabled. If local BH disable is called 3 more times, local processing remains disabled. Okay, makes sense. Processing is not re-enabled until the 4th call to local BH enable. These functions accomplish this by maintaining a per task counter via the preempt count. Interestingly, the same counter used by kernel preemption. When the counter reaches 0, bottom half processing is possible. Because bottom halves were disabled, local BH enable also checks for any pending bottom halves and executes them. Cool. The functions are unique to each supported architecture and are usually written as complicated macros in asm-soft-irq.h. The following are close C representations for the curious. This is like kind of like what it would be to implement one of these. All right, so you just increment preempt count. Enable will also probably start doing the soft IRQs too, like right here. Okay. But these calls do not disable the execution of work queues. Because work queues run in process context, there are no issues with asynchronous execution, and thus there is no need to disable them. Because soft IRQs and tasks occur asynchronously, say on return from handling interrupt, however, kernel code may need to disable them. With work queues, on the other hand, protecting shared data is the same as in any process context. Oh, that's the reason why they said work queues are simpler. Okay, makes sense. Conclusion. In this chapter, we covered the 3 mechanisms used to defer work in the Linux kernel: soft IRQs, tasklets, and work queues. We went over their design and implementation. We discussed how to use them in your own code, and we insulted their poorly conceived names. Yes. For historical completeness, we also looked at the bottom half mechanisms that existed in previous versions of the Linux kernel, BHs and task queues. We talked a lot in this chapter about synchronization and concurrency because such topics apply quite a bit to bottom halves. We even wrapped up the chapter with a discussion on disabling bottom halves for reasons of concurrency protection. It is now time to dive headfirst into these topics. Chapter 9 discusses kernel synchronization and concurrency in the abstract, providing a foundation for understanding the issues at the heart of the problem. Chapter 10 discusses the specific interfaces provided by our beloved kernel to solve these problems. Armed with the next 2 chapters, the world is your oyster. I sure hope so. Thanks, everybody.